Hi everyone, my name is Kashvi. My mentor on this project is Tatiana, and today I'm thrilled to share a project I'm deeply passionate about: how stress affects heart rate variability and neural activity in adolescents. I've always been fascinated by how stress affects our bodies, but especially the teen body, which is still developing and adapting. What sparked this project was a question: why do some teens bounce back from stress while others break down? And is the answer hidden not only in the mind, but in the signals between the brain and the heart? Before I begin, I want to thank my mentor, Tatiana, for her incredible guidance throughout this project. Your support and insight made this research possible. So, why focus on teens? Because adolescence is arguably the most neuroplastic, emotionally intense stage outside of early childhood. Brain regions responsible for emotion, decision making, and memory, such as the prefrontal cortex, amygdala, insula, and hippocampus, are all still maturing. The vagus nerve, which serves as a critical two-way highway connecting the brain, heart, lungs, and gut, more on the vagus nerve later, are also developing during this period. Teen stress is rising, and research shows adolescents report stress levels equal to or higher than adults. Yet, most traditional measures only assess behavior rather than physiological function. That's why physiological measures such as heart rate variability and EEG can be transformative. But to really understand adolescent stress, it is crucial to distinguish between acute and chronic stress because they activate endocrine systems differently and have different long term consequences. Acute stress, let's take a look at acute stress. Acute stress is short term and adaptive, like during a timed test, a speech, or a big game. The sympathetic nervous system triggers the flight or fight response during the sympathoadrenal medullary system, releasing adrenaline, while the hypothalamic pituitary adrenal axis causes a quick surge of cortisol. Heart rate, blood pressure, and alertness rise. EEG beta activity spikes, showing intense focus. With enough recovery, this type of stress can actually strengthen resilience. Chronic stress, on the other hand, is when these systems stay activated for weeks or months due to the ongoing academic pressure, sleep deprivation, or family tension, or more. Cortisol levels remain elevated. The hippocampus shrinks, prefrontal cortex regulation weakens, and the amygdala becomes overactive. Heart rate variability drops as parasympathetic control fades. Over time, this allostatic load, the body's cumulative wear and tear, raises the risk of anxiety, depression, and cardiovascular disease. By monitoring the following: cortisol levels, heart rate variability, EEG brain activity, Galvin skin response, pupil dilation, blood pressure, and neuroimaging, such as fMRI or MRI scans, we can actually catch the warning signs early, before stress leaves lasting damage. At the center of this research is the autonomic nervous system. It is the foundation here. It runs in the background, regulating heart rate, breathing, and digestion, things we don't consciously control. It is made up of two branches: the sympathetic nervous system, which triggers the fight or flight response by increasing heart rate and blood pressure, and the parasympathetic nervous system, which promotes rest, digestion, and recovery. These systems don't oppose each other, but instead work in harmony. And that harmony, that balance, is measurable through heart rate variability, or HRV. Now, heart rate variability came up many times. But what even is heart rate variability? That's what we're going to be talking about next. Heart rate variability is the millisecond variation between heartbeats, a precise measure of how well the autonomic nervous system balances the sympathetic fight or flight activity and the parasympathetic rest and digest control. A high heart rate variability signals strong vagal tone and nervous system flexibility. It's linked to emotional regulation and lower cardiovascular risk. A low HRV, on the other hand, reflects chronic stress and sympathetic dominance, often preceding anxiety, depression, and heart disease. During exercise, heart rate variability drops as sympathetic drive spikes. This is the stress response. With training and recovery, HRV rebounds, showing improved parasympathetic function as shown in the image. Um, Now we've been discussing about the vagus nerve along this presentation. Let me give a full lowdown on the vagus nerve. The vagus nerve, cranial nerve X, can be thought of as a superhighway that facilitates continuous communication between the brain and vital organs. Originating in the brainstem, the vagus nerve serves as the primary conduit body-brain superhighway. Afferent signals slow the heart, while afferent fibers deliver organ feedback to the brain. Heart rate variability serves as a non-invasive index of vagal activity, offering insights into parasympathetic function and overall physiological resilience. Now, let's take a closer look at the brain. When we're stressed, you can actually see it in the brain. EEG scans show a surge of activity in the amygdala, which basically constantly looks for threats, and in the anterior cingulate cortex, which helps process conflict and emotions. At the same time, neurons in the frontal-parietal control network, the system that supports focus and decision-making, start firing out of sync. When this network loses rhythm, it becomes harder to stay calm and attentive. Under normal conditions, the prefrontal cortex maintains top-down control, meaning higher-level brain regions regulate emotional and sensory responses. This balance allows us to focus on tasks even when there's distraction around us. But when stress hormones like cortisol and norepinephrine rise, that regulation weakens. Emotional centers take over and the brain shifts into bottom-up dominance, where instinctive reactions override rational control. We can even see this shift in heart rate variability. When top-down control falters, heart rate variability decreases, showing parasympathetic nervous system isn't effectively calming the body. If this happens repeatedly, especially during adolescence, it can breach brain circuits, making emotional regulation harder over time. That's why combining EEG and HRV is so powerful. Stress doesn't just feel overwhelming, it leaves a measurable imprint on the brain and the body. This image over here shows the visual processing pathways and how top-down control shapes perception. The dorsal pathway, in red, helps to locate objects in space, while the ventral pathway, in blue, identifies what those objects are. Higher brain areas like the frontal eye fields send signals back to visual regions, priming us to notice what we're looking for, like tuning your brain to spot your keys when you're searching for them. So stress is more than just an emotional state. It's a breakdown in the brain's control systems, and our data shows exactly how that happens. So, what does the research tell us? Research has shown us that teens with lower heart rate variability under stress often report higher anxiety and lower emotional regulation. Chronic stress reduces prefrontal cortical activity, making it harder to manage emotions, while strong vagal tone is associated with better coping, improved mood, and enhanced cognitive performance. Um, In closing, I learned that stress is not just an emotion. It leaves measurable fingerprints on the brain and the body. With the right interventions, these patterns can be rewired for resilience, especially during adolescence. Thank you for listening.